Greetings and welcome to the 19th Linear Algebra Clinic. Today's clinic is going to cover three problems dealing with the range and kernel of a linear transformation. All right, so let's jump right in. We're given a linear mapping from R4 to R3. We want to find a basis and dimension of the range and the kernel for this transformation. So let's start with the kernel. Right, so recall that the kernel of a transformation is the set of all vectors that map to the zero vector. So what we want to do for this is take the transformation of an arbitrary 4-vector right? So that's going to equal, of course, this. And we want to set that equal to the zero vector of the codomain, which in this case is the 3, 0 vector. Right, well, now, of course, we have a system of equations. So we know how to solve this. We're going to set up our matrix, our coefficient matrix. And there's no need to augment it with 0, 0, 0, right? Because that column is not going to change when we go ahead and row reduce this. So when we do row reduce it, this is what we get. Right now, right, what this first row is saying, I'm going to do this in a different color, right, is that we have x plus 2z minus t equal to 0, and then y plus z minus 2t equal to 0. So first one, we see that x is equal to negative 2z plus t. Y is equal to negative z plus 2t. So the kernel of f is the set of 3 vectors. I'm sorry, the set of 4 vectors. Let's say negative 2z plus t. I'm going to leave those variables alone. Negative z plus 2t, zt, right, such that z and t are any arbitrary real numbers. Now notice what this means. Let's call this set K. Let z be 1 and t be 0. Then we get this vector here. Now let z be 0 and t be 1. Then we get this vector. This set clearly spans the kernel of f. We also know it's going to be linearly independent. Right? You can verify that. So that set forms a basis for the kernel of F. This means that the dimension of the kernel, which is called the nullity of F, is 2. Now the range, well, it's just the set of outputs, right? So it's going to be the set of 3 vectors of this form. Right? Such that all of these variables are real numbers. Right? Now, sorry about that. Now, let's call this R. Right, so we have a set of 3 vectors. What we're going to do is set up vectors of coefficients of each of the variables, right? So we did X, here's Y, coefficients of Z, and then finally, coefficients of T. So again, this clearly spans our range. But if we take a look at the matrix we just row reduced, right? Don't you see that the columns of the matrix, right? Of course, are the vectors in R. So leading ones, column 1, column 2, which means that those 2 vectors would be linearly independent. So let's call this new set R prime. And it just consists of the vectors 1, 1, 1, and negative 1, 0, 1. This now forms a basis for range of f, which implies that the dimension of the range, which is called the rank of the transformation, is equal to 2. Okay, so I had something come up. Hopefully you don't notice the pause in the recording. Hopefully I edited it out fine. So continuing on, we're going to look at now a different linear transformation. And we're going to do the same thing. We're going to find basis and dimension for range and kernel. So again, remember, kernel is the set of all vectors in the domain that map to the 0 vector of the codomain, right? So pick an arbitrary 3 vector, plug it in to G, right? So it's going to transform it, set it equal to the 0 vector, and solve, right? So again, you should notice that we're going to have a system of equations. So let's set up our coefficient matrix. Row reduce it, and we get this. Right? So we write this out and we see that x minus 3z is 0. And then y plus z is 0, right? So obviously this means that x is equal to 3z and y is equal to negative z. So the kernel of G is the set of all 3 vectors of the form 3z, negative z, z, right, such that z is any real number. Then what we see is that the set containing the single vector 3, negative 1, 1 forms a basis for the kernel. This, of course, then means that the nullity of the transformation is 1. Okay. Now for the range, using a similar argument from above, the range of G is the set of all vectors of the form x plus 2y minus z, y plus z, x plus 2y minus 2z, such that x, y, and z are real numbers. right? And we'll find that R equals a set of 1, 0, 1 and 2, 1, 1 forms a basis for range of R, or range of G rather, which means that the rank of G is equal to 2, right? And we got the basis, remember, from row reducing this matrix up here, right? And we see that's the first two columns that are linearly independent. And we have one more. This one is a proof. So we want to suppose that we're given a linear mapping F with kernel W. And we're also supposing that F of V is equal to U. That, I apologize, should be I think it should be, no, I'm sorry, that's right. This order needs to change. I apologize. So this should be V into U as such. All right, so mapping from V into U as kernel W and F of V is equal to U. We want to show that the coset V plus W, which is V plus W such that W is in W, right? So such that W is in the kernel, is the pre-image of U. Or the pre-image, pre-image of U, right? In other words, F inverse of U is V plus W. So what we do, let's suppose that some element V prime is in F inverse of U. Then this means F of V prime is equal to U, right? That's what it means to be inverses. Which means that F of V prime minus V is equal to F of V prime minus F of V, which equals U minus U, right? Which is 0. This means that V prime minus V is in the kernel. Therefore, V plus V prime minus V equals V prime is in the coset V plus W. Which means that F inverse of U is a subset of V plus W. It's a subset of the coset. Now let's suppose that V prime is an element of the coset. right? So what this means is that v prime is equal to v plus w, right, for some w in the kernel. Then f of v prime is equal to f of v plus w, right, which equals f of v plus f of w because it's a linear mapping. That equals u because f of w is 0, right, in the kernel. So what this means is that v prime is in the preimage of u. This means that the coset is a subset of the preimage. Therefore, the preimage of u, or the preimage, is equal to the coset, which is what we wanted. So that will do it for today's clinic. Next time, we will finish up looking at linear transformations by looking at how we can represent a transformation as a matrix. I thank everyone for attending. Thank everyone for watching. See you in the next